In this video, we're going to talk about the growth of functions. In particular, we're going to introduce a concept called Big O notation. Now, in computer science, we find some things very useful in programming, and I'm going to boil it down to the concept of bounds. In other words, having upper bounds and lower bounds. And what Big O notation is going to do for us is help us start to establish bounds. Okay, so let's kind of look at it. Let f and g be functions from the set of integers or real numbers to the set of real numbers. And we say that f of x is big O g of x if there are constants c and k such that the absolute value of f of x is less than or equal to c times the absolute value of g of x whenever x is bigger than k. So this notation that I just read just a second ago, this underline notation, what we're defining here, f of x is the big O g of x. That's how we are saying that sentence. Okay. We also say that c and k we have the phrase witnesses to describe those two magic constants. Okay, so this is actually really well shown within a picture. So here's from the book, the picture that is kind of displayed here. So we have this idea that we have a g of x, that by itself it's smaller than f of x, but we can make it bigger than f of x if we multiply it by a constant. So it's higher than f of x, but after a certain point. So that magic point where it finally is bigger than f of x, that's k, and the magic c that makes it happen, that's the constant c. So as you could kind of tell, there's a lot of different constants that could make that work. By constant, I'm talking about big C values that we could multiply and make that work. So that is important note number one down here. If one pair of witnesses is found, there are an infinitely many pair of witnesses. We can always make K or C larger and still maintain the inequality, meaning that if we happen to have C prime and K prime, such that C prime is bigger than the C we already have, and K prime is bigger than the K we already have, then it's possible to go ahead and keep this inequality. F of x is still going to be smaller than, so according to the big O notation, smaller than or equal to C times the absolute g of x. But that's still going to be less than or equal to C prime times absolute g of x. So it doesn't change the inequality at all. It's still trapped in the way we need it trapped by the definition of big O. All right. This notation where you have f of x equals big O g of x, that is an abusive notation. So they actually make a point of saying that this is an abuse of notation. And we don't really say that. Some people do when they're being lazy, but as the textbook will avoid saying it that way. And usually we drop the absolute value because we're often working with positive functions anyways, like we're looking at when it's positive value, so we're not worrying about having to keep the absolute value on there, which is nice because the absolute value can kind of be a bit annoying when we're working with functions. Okay, so let's just look at an example of how kind of simplistically this can be done. All right, so we have f of x equals x squared plus 2x plus 1. And we want to show that it is the big O of x squared. Okay, in other words, I want to find some magic C, some magic constant, that when I multiply it by x squared, it's bigger than f of x after a certain point. Okay. Now we could graph this, and we will, but it's possible to do it without graphing, and I want to show you how. So the way you would start it is you would start with f of x. And we want to trap this. We want to make it an inequality. So the easiest way to make it an inequality is kind of figuring out where we're heading. I'd like to have some, oh, I just realized I didn't put absolute values. Honestly, I don't need absolute values for an x squared. X squared is always positive. So I'm not worried about it. But I want it to have an x squared in it. So here's the easiest trick. I'm going to take and say, well, with x squared, these two are clearly equal to each other. But if I say 2x squared, 2x squared is definitely going to be equal to bigger than 2x once x gets big enough, right? Once I hit a certain point, x is going to be big enough, and we're going to be safe to say that that's bigger, right? In fact, the x that's going to make it big enough is 1. The minute we hit 1, everything I plug in for x, it's going to be bigger when I square it, okay? And then same with the 1 here. I could go ahead and put an x squared in for that, and I'm definitely safe, right? I'm definitely safe. So first thing I want to mention is that x does need to be bigger than 1 in order for this thing to work, what I just wrote here, mainly because of, here, let me highlight it, this one. When x is smaller than 1, that's not the case. This inequality does not hold, okay? When x is squared, it's not bigger. But when x is bigger than 1, it does work. All right, now this happens to equal 4x squared. And that's it. That's our constant. So we just found our constant. That's 4. So C needs to be 4 at least. And K needs to be 1. That's the magic X value that makes this thing hold. So there's our witnesses. Okay. And I've just shown that this inequality, I'm sorry, this function f of x here is less than or equal to this function times x squared. I'm sorry, that constant times x squared. So I've done the a big O definition. Okay, I do want to look at the graph really quick. And in fact, since these are pretty easy to graph, I think we could just kind of do a decent rough sketch. Here, I'm going to zoom out a smidge. All right, give myself some space. Okay, so x squared plus 2x plus 1, that actually factors into x plus 1 squared. And that is a parabola with a vertex at -1, 0. Okay, or you could just say that you definitely see that it goes through the point -1, 0, right? Plug in -1, we're going to get 0 for f of x. All right. And it also goes through the point, or I should say it has a y-intercept of 0, 1. Okay. Now, this parabola kind of looks like this. So this is f of x. All right, now let's graph g of x. So g of x is just x squared. So it starts at 0, 0. And it goes through 1, 1. And then 2, 4. And so forth. I kind of, sorry, trying to draw it with the same. All right, it's going to look something like that. Okay, now in order to make g of x bigger than f of x, I need to change this to be 4x squared. So 4x squared means at the point 1, it's going to go through when x equals 1. Here, sorry, let me label this. This is g of x, which is x squared. Okay, sorry. So at 1, 4, that's the new multiplied version of g of x. So that looks like this. And that magic point where they cross each other, that happens at x equals 1, which is our k value, k of 1. And there we are. So this is this skinnier graph here. This is 4 times g of x, which is 4x squared. And it does eventually get bigger than f of x after a certain point. So there you are. That's how we kind of roughly graph that to display what's happening. All right, let's, we'll do some more examples, but there's a few things we want to just kind of discuss really quick before we do that. First of all, I did want to note here before actually I get to that next statement here. I want to note that we could have gone the reverse direction. In other words, I could have said that g of x is big O of f of x for this exact same function, where g of x is x squared and f of x is x squared plus 2x plus 1. So I could have reversed the order that I wrote the big O in, and I could have still trapped it. I would have been able to still do the same game of trapping. I'd probably have a different C and a different K, but that's okay. I'd still be able to trap it. And when that happens, that means that g of x and f of x are what they call the same order. Are of the same order. So we could redo it. We can do it in the reverse direction. Okay. Let's go ahead and look at this next statement. So when f of x, in fact, I want to zoom in a little bit. Okay. When f of x is big O of g of x and h of x is a function that has larger absolute values than g of x, then it follows that f of x is big O for h of x. And the reason is, if it happens to be that the absolute value of h of x is bigger than g of x, that's what they say, right? Right, that's what they said. Then it's going to follow that f of x is going to be, we already know it's big O for g of x. It's big O for g of x. But since h is always bigger than g of x, it's very easy to say that this is true. That c times h of x works. So there it is. We've just shown that this is less than or equal to this. So by definition, f of x is big O of h of x. So if we have a function that's always bigger than 1, we can go ahead and apply the big O definition to it. Okay, let's try another example here. Let's show that 7x squared is big O of x cubed. Okay, so this one isn't too complicated because if we look at when x is bigger than 7 in particular, when x is bigger than 7, okay, when that happens, 7x squared is going to be less than x cubed, right? So if x happens to be 8, we would have 8 cubed on this side, 8 squared on this side, and then times a 7, which is a little bit smaller, right? So we have 7 times 8 times 8 less than 8 times 8 times 8. So this statement holds true. Here, let me write out what I just said. If x happened to be 8, clearly, that works, right? The inequality holds. So if we're big enough, this statement is absolutely true. So that means that I could say 7x squared, which is my f of x here. That is f of x. This is g of x. 7x squared is less than or equal to 1 times x cubed. So there's our magic c. C is 1. And our magic k value is the restriction we placed on x, that x has to be bigger than 7. So when k is 7 and bigger, or bigger than 7, yeah, 7 and bigger, because we're saying it can be equal to, we're good to go. So there's our witnesses, our magic pair of numbers that make it work. Let's look at an example where it doesn't work. So in this one, they're saying n squared is not big O of n. Okay, so let's look at what happens if we assumed it did work. Let's say that we can find some magic c that when we multiply it by n, it's going to be bigger than n squared. Okay, and this is for this magic n value of k. We'll deal with that in a second. Well, here, actually, I'll state that. So let's say this happens for whenever we're plugging in values that are bigger than the magic k number. Okay, so n is not going to be 0 because we're working with positive constants right now. We know that that's the type of numbers we're working with. So I could divide both sides by n, which means that that n needs to be less than or equal to c. Well, that's a problem because this contradicts this statement that n is bigger than k. So if I say that n is bigger than 4, and then later on I say n can't be bigger than or equal to 5, well, that's a problem because I'm already saying that this happens anytime. It has to. When n is bigger than k, this statement holds. Well, this statement ended up producing something that kind of put an upper restriction, which is problematic. That's a contradiction. So that won't work. All right. So we do have the ability to kind of look at a generalization of polynomials. So I want to establish right here that this is a polynomial. Right? X cubed plus 3x squared plus x plus 5, right? Polynomial. It's just this string of x's to different whole number powers, and they are usually going in descending order. Okay. And then all of our numbers in front are real numbers, so they're well behaved. Whenever this type of polynomial exists, the big O, the f of x, this f of x is the big O of x to the n. So the largest degree of that polynomial, that's going to end up being the magic g of x that works for f of x. Okay, now we're going to show this is true in general. So we're going to prove this. And it uses a concept that gets used a lot when you work with inequalities, and it's called the triangle inequality. And I'm going to show you what it is, and you're going to be like, yeah, it's kind of obvious. If I told you that the absolute value of x plus y, two numbers we're adding together and take their absolute value, okay? Pick two numbers in your head, 2 and 3, great. This is always going to be less than or equal to the absolute value of the numbers individually and added together. So if I pick 2 and 3, clearly the absolute value of 5 is less than or equal to 5. But if one of the numbers happens to be a negative and we add them together first on the left side, clearly that's going to end up giving us a bigger number on the right side when you take the absolute value of the negative first and then add them together. So the triangle inequality is a nice nifty inequality we're going to kind of use a lot when we're proving things with inequalities. Okay, so here we go. This is our f of x. Our f of x equals a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus ... a sub 1 to the x, a sub 1 times x to the 1 plus a sub 0, no x. Okay, so I'm going to use the triangle inequality to break up the absolute values. Now, when I do that, I'm going to take the absolute value, and I'm going to go ahead and just pull the x to the n's out of the absolute value. And the reason is these are going to be positives. We've just been talking about that. What we're plugging in for x is positive numbers, so I don't have to worry about them being in the absolute value. They can be in the absolute value, but it's not necessary. What is necessary are the numbers, the coefficients that are in front of the x's. Those potentially could be negative, and therefore they need to stay in the absolute value in order to make this work. Sorry, I should have said less than or equal to. That's the triangle inequality. Sorry about that. Okay, so now that that's true, I'm going to use a little bit of algebra here. I'm going to factor out x to the n from every term. So in the first term, I'm just left with the absolute value of a to the n. But in the second term, I'm left with absolute value of a sub n minus 1 over x, because this only has an x to the n minus 1, right? So it can only give me n minus 1, and I'm taking out n. So I need to have 1 in the denominator in order to compensate. So that means all the rest of them are going to have fractions, basically. So this term here, I'm going to be left with a sub 1 divided by x to the n minus 1, because that can only give me one x, and I'm dividing or pulling out an x to the n. And then the last term has no x's to give, so it's divided by x to the n. Okay, really quick, in case that just felt a little too fast, let me do an actual example. Okay, let's say I have x cubed here. Let me actually put a number in front. 2x cubed plus 3x squared plus 4x plus 5. Okay, I'm going to factor out an x cubed. So the first term is just going to be a 2. But the second term, that's going to be 3 over x, because it only has an x squared to give me. Here, this is going to be a 4 over x squared, because it only has an x to give me. And this is going to have a 5 over x cubed. So when I factor out that lead variable, all the rest of them are going to have fractions except the very first number. All right, that's what I just did. Okay, here, let me erase it. I don't have room to leave this. Unfortunately, I have to write a little bigger. Maybe you can leave that. Okay, back to the statement. Now, here is the magic. I'm going to, again, create another inequality and say that this is going to be less than dropping all of those fractions. I'm going to just drop those fractions now. Oops. Because if I'm dividing by a positive number, if I get rid of those fractions, oops, there should have been dot, dot, dot there. Dot, 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 plus a sub 1 plus absolute value, a sub 0. Okay, there we go. So dropping the fractions actually means I'm working with an even bigger number. And this is just a gigantic constant, which I can call C. So I've just shown that f of x is less than or equal to C times x to the n, which is the g of x for this big O notation. So we did it. We're done. And in this problem, k needs to be bigger than 1 in order to work. So x needs to be bigger than 1 in order for this statement to work, because fractions aren't going to be smaller if I'm not using a 1. In other words, if I'm putting fractions into the denominator, that's a problem. Then this statement from here to here doesn't work, right? If I have a 1/2, clearly, if I drop the 2, 1 is bigger, right? That's bigger than this. If I drop the 2. But if this is 1 over 1/2, this is not bigger. That's not true. This is bigger. So what's in the denominator needs to be a whole number or a number bigger than 1. So that is got to happen. So k is going to be 1 in this. And c is going to be this absolute value of the sum of these coefficients. I don't know why I put the parenthesis. That's unnecessary. So that's C and that's K. And we're done. We've shown by the definition that that is big O in general for any polynomial. Okay. So now let's do some generalized examples. Use big O notation to estimate the sum of the first n positive integers. Okay, so if you're adding up integers, that's 1, 2, 3, dot, 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 down to n. So I'm just adding them up all the way up to n, whatever n is. Okay, so let's use our trick here. I can make all of those instead say that they are all definitely smaller than n, since n is a bigger number. And how many of these do we have? We have n of them. So this becomes n times n, or n squared. So it's big O of n squared. All right. And in this case, I'm going to let C is going to be 1 because there's no number in front. And as long as N is bigger than K, we're good to go. I'm sorry. As long as N is bigger than 1, we're good to go. So this works as long as N is bigger than 1. That's our magic number for K. So there's our witnesses. And here is the big O that we're using. So let's try another one. Factorials. So I don't remember if we've talked about factorials, but if you haven't, let's review it really quick. A factorial is when you put the exclamation mark and then you multiply each term from that number down. So 5 factorial is 5 times 4 times 3 times 2 times 1. 3 factorial is 3 times 2 times 1. All right. So if we're working with any factorial, we'll go ahead and call that n factorial. And n factorial then is n times n minus 1 times n minus 2, all the way down to 1, right? Like it's just going to always get down to the same numbers at the end. Okay, so there's n factorial. So let's start with this. N times n minus 1 times dot, 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 times 2 times 1. This is always going to be less than, let's use the same trick we used above, n times n, which means we have, again, there are n of these, but we're multiplying this time. So that's n to the n. So there we are. There's the big O. C is again going to be 1. And this inequality holds as long as n is bigger than 1. So there's our K value. And there's the big O that we can use for that. All right, let's try another one. Log notation. Now this one's actually surprisingly easy. So we want to estimate log of n factorial. Well, we just showed that n factorial is less than or equal to n to the n. We just showed that. So if we take the log of both sides, that must be true, right? But log property says that I can put the n in the front when I have an exponent. So there we go. There we go. So this is our g of x here. So that's our big O, n log of n. C is still 1. Okay. And K needs to be 1 as well, because as long as we're looking at non-fractions, we're good to go, not numbers smaller than 1. So that came out very easily from what we just did right above it. Okay, so the book does have, here, let me zoom out a bit, a nice little picture that shows the different relationships between the functions, just so you can kind of see which ones are bigger versus smaller. And then they do some nice little statements about the functions that are going to be true. So for instance, if we happen to be working with D and C as exponents, okay, the smaller one works as big O, but the larger one does not. Okay, so it makes sense when you're working with an inequality that the larger one could be a problem. And then they kind of go through some various statements. I'll let you read that to yourself. I just went ahead and included it so it would be here in the notes to kind of refer to when you work on homework. Okay, so I want to look at the growth of the combinations of these, meaning like doing different combinations of these statements here. All right, so this one is a theorem that says if we are working with f sub 1 and it happens to be big O of g sub 1, and then we have an f sub 2 that is big O of g sub 2, then if we added those two functions together, they are big O of whichever is the maximum of either G1 or G2. Okay, so we're going to prove this. And again, we're going to, oops, sorry, let me switch to my red pen. Again, we're going to use the triangle inequality. Okay, so here's where we're going to start. We're going to start with our two functions. Actually, hold on. We're going to start with the assumption that that F1 and F2 are big O for G1 and G2. Okay, so F sub 1 of X must be less than or equal to C sub 1 times G1 sub 1. And same with F sub 2. We'll call it C sub 2 for G sub 2. Okay, and this is for C1, C2, and then a magic K1 and K2, which are some sort of constants. So here, I'm just going to call them real numbers. Okay, so this has to be true because we're assuming that's the case, that these are both big O functions for G1 and G2. Okay, now I'm going to look at adding F1 of X plus F2 of X. Okay, so if I add those two together, all right, according to the triangle inequality, I could break them up. And this happens to be bigger when I do, or possibly equal to. Okay, but both of these are trapped by constant C1 okay, but now if I let G be the maximum of these two, oops, G1 or G2, whichever one's the bigger one, then this is going to be C1 times G of X instead, plus C2 times G of X instead, which is just C1 plus C2 times G of X. So there is my magic C value. I'm kind of running out of room, sorry. So this is C. All right. And then we pick whichever K is bigger. And we've done it. We've shown that when you add them together, you can find a big O based on the bigger of G1 or G2. So we're done. Squeezed it in. Okay, and then I just included these two additional statements, which are kind of obvious when you look at them. The corollary says that if you are adding, you have two functions that are both big O of the same G of X, then you can add them together, and that addition of functions is the big O of G of X as well. And then again, if you have two separate ones with two separate big O G of X's, you can multiply them together. We're not going to prove those. We'll go ahead and assume that they work and use them as we go through the homework.